All right, so welcome everyone to the third episode of the 5th season of the Isogeny Club. Today we are lucky enough to have Gioella Lorenzon giving her talk. She's a PhD student at the KU Leuven. And yeah, she's gonna talk to us about generalized class groups and elliptic curves with level structure. So please, Gioella, the floor is yours.
Thank you, and thanks to you and Maria for inviting me today. I really appreciate it. So as you said, today I'm going to talk about generalized class group actions on oriented elliptic curves with level structure, which is joint work with Sarah Arpin, Wouter Castryck, Jonathan himself, and Vercauteren. So let me start with a bit of motivation. So as I said, I'm going to talk about orientations and level structures. Orientations are now a very well-known and widespread framework that essentially allows us to transport characteristics of the ordinary elliptic curve and isogeny world into the supersingular setting. So for example, they allow us to have commutative group actions in the supersingular setting as well. And we also find, again, volcano-like structures in the isogeny graphs of oriented supersingular elliptic curves. Level structures, on the other hand, have emerged, for example, thanks to their nice mixing properties of the graphs that they define. And they've also recently been used to systematically study reductions between security assumptions underlying common isogeny-based cryptosystems. And there have been some examples mixing the two frameworks, orientations and level structures. And among these examples, I want to cite Seaside with full level structures, which was studied in a recent paper by Galbraith, Perrin and Voloch. And for today, the goal will be try to understand whether such examples can fit into a bigger story and hopefully show that there can be a bridge between orientations and level structures. So I will, in today's talk, as I said, first start with introducing orientations, level structures, and class group actions. And the main two examples that we're going to use are SCALLOP and Seaside with full level structure. These two examples will lead us all the way to discovering some sort of bigger story into which they embed nicely. And so this will lead me to talk about generalized class group actions. I will then define a large family of such generalized class group actions, class groups and their actions on certain sets that we're going to discover. And I'm going to state one theorem about such family of generalized class groups. And under the light shed by this new theorem, I would like to go back to the starting examples and sort of reinterpret them. And finally, I will conclude with some very brief security comments. So I will start by fixing some notation first. So small k will be a field of prime characteristic. Let's take it bigger than 5. E will be an elliptic curve defined over such a field K. Capital K will be an imaginary quadratic number field. And in this field, we will take some orders, which will usually be called O or O prime. And recall that orders are subrings of K that are also free Z modules of rank 2. F will usually denote an integer, which will be the relative conductor of some suborder O prime of some other order O, which is namely the index of O prime inside O. Yeah, this conductor will also always be taken co-prime to the prime characteristic of the base field. Let me now recall the definition of the class group of an order O. We take the group of invertible fractional ideals of O, and we quotient it out by the subgroup of principal fractional ideals of O. I will use this Gothic font to indicate an invertible ideal of an order O, and I will use brackets when I want to indicate a class for that ideal in the class group of O, or maybe later on some other more general notion of class group. N of A will indicate the norm of A, which is the index of the ideal A inside the order. Now, as promised, let's talk about orientations. So let's recall the definition of a primitive O orientation on an elliptic curve E, which is an embedding iota of the order O inside the ring of endomorphisms of E. If the orientation is primitive, then we need to ask that iota cannot be extended to any strictly bigger order O prime containing O. Primitive is in brackets because I will probably often forget to say the word primitive, but all orientations that we are going to mention today will be primitive. LKO will be used to indicate the set of elliptic curves defined over K together with a primitive O orientation up to oriented isomorphism. And an element in such a set will always be some E together with some iota. Now, recall also that an isogeny phi from an elliptic curve E together with an orientation iota induces an orientation on the codomain that you see defined in this formula here, and I will always indicate as iota subscript phi the name of the isogeny. Now, up to some conditions that I'm not going to say explicitly, the class group of an order O acts freely and essentially transitively on the set of primitively O-oriented elliptic curves over K, where this essentially is there because depending on some splitting behavior, or on the splitting behavior of the characteristic of the base field K, then we might have to retouch the definition of this LKO to make the action really transitive, but it's a bit of a technicality that does not concern us today. So let me remind you of how such an action comes about. So if we take an ideal A of our order O, then we can define the kernel subgroup of A as the intersection of all kernels of elements alpha in the ideal A viewed as endomorphisms of E through the orientation. And this defines a subgroup of E, and then up to isomorphism, it determines an isogeny, phi A, from E. This isogeny is oriented if we endow the codomain with the induced orientation by, the orientation induced by the isogeny itself. Then it is natural to define an action of the class group of O on LKO by sending an elliptic curve E together with its orientation iota, to the codomain of the isogeny defined by our class group of A, so the codomain of the isogeny of kernel, the kernel of the ideal A, and together with the orientation induced by the same isogeny. Now, I've said that the class group of O acts freely and transitively on LKO, and the action being free means that a curve, an element of LKO, it's sent to itself if and only if the class group that we are using for the action is the trivial element of the class group of O. While the action being transitive means that for any two elements of LKO, then we can find an ideal class that sends one into the other. Now we know that for suitable parameters, such an action is cryptographic, and a prime example is Seaside. There we take as base field a field of prime characteristic P, and we take primitively O-oriented supersingular elliptic curves where O is taken to be the order Z square root of minus P into Q square root of minus P. And it turns out that LKO is then a set of supersingular elliptic curves defined over FP up to FP isomorphism. And we know that the class group of Z square root of minus P acts freely and transitively on such a set. Let me now go to one of our favorite examples of today, which is SCALLOP. Again, the base field is a prime field, a prime characteristic field, and we take this time an order O prime of conductor F inside the order Z adjoint square root of minus 1, where the conductor is prime to the base field characteristic P. Then we have free and an essentially transitive action of the class group of O prime on the elliptic curves that live at the first level downstairs, let's say, of the F isogeny volcano. So in SCALLOP, we have a diagram of this shape where the top curve is primitively oriented by Z adjoint square root of minus 1. For example, y squared equal to x cubed plus x. So we have the curve of Galbraith 1728. So for example, we take this one with the O orientation given by sending square root of minus 1 into the endomorphism I, which sends a point of coordinates xy to the point of coordinates minus x and y square root of minus 1. Now notice that each curve living downstairs is the codomain of some F isogeny going from E on the top to the first level of the isogeny volcano. So we can associate to each curve EJ downstairs some F subgroup CJ of the curve on top, namely the kernel of such a descending isogeny. So what we would like to do for today is think of such a subgroups CJ as some level structure on the curve on top. So let me now give the definition of level structure. So recall that for an integer n coprime to the base field characteristic, we have that the n torsion subgroup of an elliptic curve E isomorphic to Z modulo n times Z modulo n. If we fix a subgroup of the 2x2 invertible matrices with entries in Z modulo n, then we can define a gamma level structure on an elliptic curve E as the choice of an isomorphism from Z modulo n times Z modulo n to the n torsion subgroup of E up to precomposing with some element of the subgroup gamma, which in other words means fixing a basis, call it PQ, of the n torsion subgroup of E up to base change by some matrix in gamma. Just to give an explicit example, we can think of P and Q being the points that are image of respectively the vectors 1, 0 and 0, 1 under some fixed group isomorphism phi. And let's take gamma to be matrices that are invertible and that have a 0 on the bottom left entry. So an element gamma will have this shape right here. And so we can see that the point P up to by precomposing with such a matrix gamma will be sent to some multiple A times P, and Q will be sent to combination B times P plus C times Q, which means that fixing gamma level structure here is just fixing a cyclic n subgroup generated by some point P. We call such a subgroup gamma 0 n. So going Oh, yeah. Let me give you a little some more examples, some more typical examples. You can play the same game that we've just played. And if we take now, for example, matrices with zeros, both on the top left and on the bottom left and top right corner, then the corresponding level structure will fix two independent cyclic n subgroups. If we fix the first column to be 1, 0, then the level structure fixes a point of order n. If we take the subgroup that only contains the identity matrix, then the level structure will fix really a basis of n torsion, and we call such a level structure a full level structure. Now, going back to SCALLOP, as we said, we would like to think of some F subgroup Cj of E as level structure on E, and I think you will now agree with me that this is gamma 0F level structure. We are really fixing a subgroup of order F. And the question would be now whether is it possible to translate the action of the class group of O prime on the curves downstairs, EJ oriented by O prime, into an action on the curve up top, the curve E, oriented by O, but now equipped with gamma 0F level structure. And it turns out the answer is yes, and we can make it actually quite explicit. So if we take ideals, let's call them A alpha beta generated by F squared and F times alpha plus beta square root of -1 into the order O prime of conductor F into Z adjoint square root of -1. And we take these alpha beta as the coordinates of point on the projective line with entries in Z modulo F. Then the classes of these ideas form all of the class group of O prime. And if we let our subgroup Cj to be generated by some point Pj, then the action of the ideal class of A alpha beta consists in sending the subgroup generated by Pj into the subgroup generated by alpha Pj minus beta I of Pj. Now, this looks quite specific and also a little bit mysterious. So the idea now would be to try to understand whether this translation could be made a little bit less mysterious and whether it could be part of a bigger story, hence why our conspiracy cat in the slide. So there is some evidence that that there could be a bigger story going on here. And for example, going back to the work by Galbraith, Perrin and Voloch, but there's also a similar observation made by Colo and Coel. There is indeed a free and transitive action on curves primitively oriented by Z square root of -1, Z square root of -P, together with a full level structure. And the action is by some notion of class group, that is the ray class group. So I would like to now explain to you what the ray class group is. So bear with me a little with some more definitions and some more notation. From now on, M will be a non-zero ideal of O as well, that I will sometimes call modulus. So for any modulus M, it is a known fact that each class in the class group of O contains an ideal that is coprime with M, namely such that the sum of A and M generates the whole of the order O. Now, we can take the subgroup of the invertible ideals of O generated by those that are coprime with a fixed modulus M. We can also take the subgroup of such ideals that are also principal, and it turns out that there is a natural isomorphism between the class group of O and the quotient of such I-O of M over P-O of M. Let's just now leave this here and keep it in mind for later. And Let's see what array for a certain modulus M is. Array for a modulus M is a principal fractional ideal generated by some element alpha, an invertible element of the field K, such that alpha is congruent to one modulo the modulus M. I'm going to tell you what this means, but you can, just for completeness, but don't worry, you can also forget about it. It's not super important. So we say that alpha and beta are congruent modulo M if when we write alpha as alpha 1 over alpha 2 and beta as beta 1 over beta 2, where these alphas and beta are elements of O. Then we ask that alpha 1 beta 2 minus alpha 2 beta 1 is in the modulus M. Now you can see very easily that the rays form a group. If I multiply two rays together, then this condition will still be satisfied. And yeah, sorry, yeah. So yeah, if we take the group of rays for modulus M, we end up with some subgroup of PO of M that we call the ray group, and we will call PO1 of M. Now, this is a list of the newly introduced notation, just as a reminder. Now we define the ray class group for modulus M as the quotient now of our subgroup of invertible ideals of O coprime to M over the group of rays for modulus M. We can do something a little bit more general than this. And what we can do is to take a subgroup that stands in between, that lies in between the group of rays for modulus M and our original subgroup of principal ideas of O coprime to M. And if we now quotient IO of M with such a subgroup that we call a congruent subgroup, we end up with what we call a generalized class group. Now, we can see some examples and notice that if we take the H to be one of the extremal cases, say, for example, we take H to be the biggest possible, then the generalized class group that we end up with is IO of M over PO of M, which, as I said a few slides ago, is naturally isomorphic to the class group of O. If we now take to be if we now take H to be the group of rays, which is the smallest possible congruent subgroup, then the generalized class group that we obtain is the ray class group for modulus M. So the class group of O and the ray class group are indeed some example of generalized class group. Let's see now an intermediate example. Let's for simplicity take a modulus to be just a principal ideal to be generated by some integer f. And let's take as congruent subgroup the following, inspired a little bit by the definition of the group of rays. We take ideals generated by some invertible element of K that is congruent modulo FO to some integer G coprime with F. And we call such a congruent subgroup POZ of the modulus FO. It turns out, and it is a bit of a classical result, that the generalized class group that we end up with is isomorphic to the class group of O prime, where O prime is a suborder of conductor F of our order O. And recall that this is the setting of SCALLOP, where we have O prime suborder of conductor F of Z adjoint square root of -1. And we have the class group of O prime that we can now view as a particular case of a generalized class group acting freely and transitively on primitively oriented ellipticals by O prime. Now, notice that a congruent subgroup is a subgroup of PO of M, which implies that in general, generalized class group is bigger than the class group of O. This means, however, that there is still a well-defined action of a generalized class group on the set of O-oriented elliptic curves, which works precisely in the same way. But what we do is we take a class group of an ideal A, we send it first to the class of the same ideal now in the class group of O, thanks to the natural surjection from class group of H to class group of O, and then we apply the action as usual. However, if we take the congruent subgroup to be strictly smaller than PO of M, then the class group that we obtain, the generalized class group, will be bigger than the class group of O. This means that the action will no longer be free because we are acting with a bigger group on the same set. So we will end up with having non-trivial elements, non-trivial ideal classes acting trivially. So this means that we are left with some room to act freely on a bigger set than LKO. And to make the set bigger, the idea is to further distinguish its elements by adding some extra information that would be a slightly more general notion of level structure than the one we've seen at the beginning. Before saying what such a notion of level structure is, let me first state this lemma, which says that if M is an invertible ideal co-prime to the base field characteristic, then the kernel subgroup of M is isomorphic with the quotient of O over M, not only as groups, but also as O modules. For example, when the ideal that we take is some principal ideal generated by an integer coprime to P, then this is telling us then the n-torsion subgroup of E is isomorphic, as we know, as Z modulo N times Z modulo N, but really as O modules as well. More generally, we have that the M subgroup of E is isomorphic to Z modulo N times Z modulo B for some integers A and B, with B dividing A, and really not just this group but also as O modules. Now, for our slightly more general definition of level structure, let's take gamma to be now a subgroup of the general linear group of the quotient O of M. And a gamma level structure on E will be now a choice of a group isomorphism from O over M to the kernel subgroup of E, up to precomposition with elements of gamma, and postcomposition with oriented automorphisms, which in other words means then fixing a basis PQ of EM up to base changes by gamma. All right. We fix now Y gamma to be the set of primitively O-oriented curves together with gamma level structure up to oriented isomorphisms. Now, before continuing, let me give you a short recap. We defined generalized class groups acting on LKO, but they are not acting freely. To hope for a free action, the idea is to enlarge LKO, and we enlarged it now to Y gamma, where we attached level structure to oriented elliptic curves. Now, I would like to define a family of congruent subgroups, find the corresponding level structure in order to have a well-defined and possibly a free action of such generalized class groups, and show you that there is a subset Z gamma of Y gamma where the generalized class groups corresponding to such a family of congruent subgroups act transitively as well. All right, so this family of congruent subgroups is inspired by the definition of the Ray class group, which I remind you is the one is a generalized class group corresponding to such a congruent subgroup P01 of M. Now the idea is to replace this one here with something a little bit more general. So what we do is we take lambda, a multiplicatively closed subset, and we define now these congruent subgroups P O lambda of M, where we ask these generators alpha of ideals alpha O to be congruent to some element lambda modulo the fixed modulus M, where lambda is some element lambda coprime to the norm of M. Lambda is taken to be a multiplicatively closed subset in order for these PO lambda of M to be groups. Now, by design, this family of congruent subgroups will contain all the examples that we've seen so far. Indeed, if we take lambda to be 1, clearly we fall back into the group of rays for modulus M, which defines the rays class group. If we take instead lambda to be the whole of the order O, then the corresponding congruent subgroup will be just PO of M, the group of invertible principal ideas coprime to M. So the corresponding class, generalized class group will be just the class group of O. We also encounter again one known example, which is the case when we take lambda to be Z and the modulus to be FO for some integer F. Then the congruent subgroup that we end up with is the one that defines the class group of O prime being a suborder of a conductor F of O. Now, we've defined this family PO lambda of M of congruent subgroups, which in turns define generalized class groups. And we would like to act on primitively O-oriented elliptic curves with gamma level structure, but the question now is, which gamma do we have to take? And the answer is quite natural. Under the intuition that the gamma level structure will have to determine some equivalence that reflects the equivalence that is established by these congruent subgroups PO lambda of M on the level of ideals. And so the gamma level structure that we need to take for this is, the subgroup gamma that we need to take for this is multiplications by elements alpha that are generators for ideals in PO lambda of M. And when we unravel the definition of PO lambda of M, then what we find is that this is equivalent to taking multiplications by elements lambda coprime to the norm of the modulus M with lambda taken in O star lambda. This O star here appears for a bit of a technical reason, but essentially it accounts for the fact that gamma level structure is isomorphisms up to post-composition with oriented automorphisms as well. Now, finally, we can state the main result of the paper. Let me first add some more notation and definitions if they weren't enough. So recall that we called Y gamma the set of primitively oriented curves with gamma level structure up to isomorphism. Now, when it makes sense, we can define a subset Z gamma of Y gamma, and when it makes sense is precisely when gamma consists of O modular automorphisms. Then in that case, Z gamma is defined to be the subset in which the level structure is not only an isomorphism of groups, but also an isomorphisms of O modules. So now you probably understand why I mentioned a lemma earlier, saying that the kernel subgroup of modules M is isomorphic to O quotiented by M, not only as groups, but also as O modules. All right, so Let's state our theorem for our family of generalized subgroups P O lambda of M. The theorem says that we have a well-defined and free and transitive action of the generalized class group of H on the subset Z gamma 0 lambda of M. And the action is defined in a way as we expect. So for the first part, it really works as usual. We send E to the codomain of an isogeny phi defined by this ideal class A. The orientation is the one induced by the isogeny phi A, and the level structure is the same level structure as in the domain, now post-composed with the isogeny phi A. Now, we can also extend this action to a free action on the whole of Y gamma, but under the condition that our lambda is contained into O star Z, where O star is units of the order O, which is usually just plus or minus 1, but in some cases it can also be more. So this was just to say that this O star Z is usually just Z, but it can be in some cases a bit bigger. Now, I would like to go back to our initial motivating examples and to revisit them in view of this theorem. So let's start by SCALLOP. Remember that for this case, we want to take lambda to be Z. Our generalized, our congruent subgroup is POZ of FO. And the corresponding generalized class group is the class group of the suborder O prime of conductor F in the order O, which is Z adjoint square root of -1. Now, the corresponding gamma level structure is then multiplications by elements, by integers lambda co-prime to the conductor F, which indeed, as we discovered in one of the first slides, is gamma 0 F. What is then now the set of primitively oriented curves together with gamma level structure? It will be primitively oriented elliptic curves together with a basis of F torsion, PQ. And PQ will be considered equivalent to lambda P, lambda Q for any lambda integer co-prime with F. Now, by our theorem, the class group of O prime acts freely and transitively now on Z gamma 0 F, where the level structure is an isomorphism of O modules. So to specify such an isomorphism, we need to fix the image of 1, which will be a point that needs to satisfy the condition that P and I of P, where I is the image under the orientation of square root of -1, a generator of the orienting order. So we want P and I of P to be a basis of F torsion, of course, up to gamma 0 F base changes. So in other words, this means that in Z gamma, we only need to specify a point on the elliptic curves, a point such that P and I of P is a basis of F torsion. And we say that P is equivalent to lambda P for any lambda integer co-prime to F. But then this means that in Z gamma, the level structure is really given by some F subgroups of E. And in the case of SCALLOP, then this really means the elliptic curve E together with kernels of descending isogenies to the first level of the volcano. So nice. This means that we've generalized correctly in the sense that our theorem does reflect what we observed in the beginning about SCALLOP. And one last question would be whether we can extend this action freely to Y gamma. the condition for this was that lambda was contained into O star Z, where O star in this case is not just plus or minus 1, because in Z square root of minus 1, we also have square root of minus 1 and minus square root of minus 1 as units. But we observed that the gamma level structure defined by taking lambda to be Z or taking lambda to be O star Z is really the same. So up to replacing lambda with O star Z, then the action does indeed extend freely to Y gamma. I have now 2 more examples, but maybe I will show one for the sake of time. Let me show maybe the case of a C-side with full level structure. Here, remember, we take lambda to be 1. The R congruent subgroup is the group of rays. Then the class group, the generalized class group that we define with such a congruent subgroup is the ray class group, as we saw. And the gamma level structure here is now really multiplications by lambda, where lambda is taken to be from the set containing just 1. So indeed, this is just the identity, and gamma is then the full level structure as we expect. Now, the set of O-oriented elliptic curves together with full level structure is what we expect. But Y gamma n has to take into account post-composition with automorphisms, and that is why we also consider PQ to be equivalent to minus P minus Q. So in the previous example, these oriented automorphisms were already taken care of by the choice of lambda, but here lambda really only contains 1. And so we have to be a bit more careful. Now, the ray class group acts freely and transitively on Z gamma n, where again, we have that the level structure is really a morphism of O modules, where O is now some Z adjoint sigma. So again, we want to specify the image of 1 that has to be a point P such that P and iota of sigma P is a basis of n torsion. Sigma in our case is square root of minus P. So really Z gamma is E together with a point P such that P and iota square root of minus P of P is a basis of n torsion. And again, we have P equivalent to minus P due to minus 1 being an oriented automorphism. Again, we may wonder whether we can extend to a free action on Y gamma n, and the answer is clearly yes, because 1 is indeed contained in O star Z. All right, let me skip this example and get to the concluding remarks about security. So we have seen that generalized class groups act on generally larger sets than Lk of O, being larger than the standard class group of the order O. And so one may wonder whether the vectorization problem becomes harder for the action of the generalized class group. And for the case of C-side with full level structure, Galbraith, Perrin and Voloch already explained that even though indeed in C-side with full level structure we are acting on a larger key space, the problem, however, reduces to standard C-side. And in our case, this is no different. In general, the vectorization problem for a generalized class group reduces to that of the class group of O. Yeah, so however, in SCALLOP, we can observe that such a reduction goes through large prime degree isogenies. So even though we are able to see how this reduction works, and really we're able to trace back to some action on subgroups of the top curve E, such subgroups have huge order and huge prime order, and they will leave over huge extensions. So really, we have no hope to really see these subgroups and to hope to solve the vectorization problem in this way. So yeah, just to conclude, then we can say that with this new framework that we've introduced, we don't have hopes to produce new crypto systems, but we see that it really gives a way to reinterpret some examples like SCALLOP and to really better understand such sort of reductions. This, I think, is everything that I wanted to say. This is a slide with references, and then thanks for the attention. If you have questions, I'll be happy to answer if I can.
Thank you. That was a great talk. Does anyone have any questions? Yeah, Mark, you can unmute.
Yeah, can you hear me?
I can.
Yeah.
All right.
Hi, Mark.
Hey, so you said this doesn't give new crypto systems, but then SCALLOP is still secure. So can you like give a condition? Can you give a condition on H for the resulting class group action to be difficult?
We do not give such a condition in the paper, but it is true that for the reduction you would have to go through some discrete logarithm and some pairing computations. So I would say that if you can make that explicit, that clear, then maybe you could trace it back to some condition on the congruent subgroups. I'm not sure whether on the congruent subgroups themselves, or if it has more to do with the choice of the order. Because for SCALLOP, really, the important thing is the order of the conductor, which is a large prime, which of course then plays a role also in the definition of the corresponding congruent subgroup. But I'm not sure what comes first.
Okay, yeah, I don't know. Just at the end, it seemed like you mentioned that there was like a clear thing that you had to do to kind of like reduce the problem to CLO. And I think for SCALLOP, it's just computing a large degree isogeny, right? So
Indeed, yes.
So maybe it's yeah, maybe there's some kind of subgroup associated to CL of H where in the like some kind of subgroup in the reduction process where you have to compute an isogeny that has this as a kernel or something. That's what I was guessing, but yeah, maybe
that
interesting.
Sounds like we could think about it. Indeed. Thanks.
Okay, thank you.
Are there any other questions? I had one again about the security. I was wondering if you looked like beyond these two examples at just like generally the level structure and trying to compare the security between different level structures. Like now that you have this sort of generalized framework, I guess you can look at like a class of problems and see which ones are harder than others. Did you look at that?
Yes, we have indeed a few more examples relating, for example, to MSIDH. But maybe I should mention one interesting paper that was mentioned also in the previous Isogeny Club talk, which is isogeny problems with level structure, which really systematically goes through studying such sort of reductions. Yeah.
Okay, cool. And have you looked Sorry, just another question. Have you looked at like constructively trying to see if you can get interesting constructions using these different level structures, or
not really. No, not really, I would say.
okay, cool. Are there any other questions? Okay, if not, then let's thank Gioella again. Thank you. That was a really great talk.
Thank you.
As you can see in the chat, everyone likes it a lot. So thank you again. Yeah, so our next episode of the season will be in 2 weeks. And Marcio Muller will give a talk on the Hessian as a lattice. I don't know if I'm pronouncing that right. Yeah, the details are on the website. And yeah, thank you again for everyone showing up, and hope to see you in 2 weeks. Let me just stop the recording.